Hi, everybody, and a very pleasant good morning to you wherever you may be. My name is Brian White from JPL's Office of Communication and Education, and welcome to this celebration of the Cold Atom Laboratory, a unique mission illuminating our quantum world. We have a wonderful panel of speakers for you today, but we want to remind everyone watching at home that this is your space program and we want you to be involved. We will have a Q&A at the end of this panel, so please ask questions in the chat. Now, if you don't find your chat right now, go ahead and refresh your page, and it will be there. To begin, it is my pleasure to introduce a distinguished geochemist and space scientist. Please welcome the director of the Jet Propulsion Laboratory, Dr. Lori Leshin.
Hello, everyone. Hi to everyone here in the room and everybody watching online. Welcome to this great celebration of 4 years of the Cold Atom Lab up on ISS. Let's give them a hand. 4 years, yes. I'm so happy to be here. You know, here at JPL, we are all about driving the frontiers of scientific discovery from space. You probably know us as the cool Mars rover people, and we are. Also celebrating this year 10 years of Mars Curiosity rover on Mars, so celebrating lots of anniversaries. But we do more than Mars rovers. We do astrophysics missions. We study our home planet of Earth, and this is a great example of driving the frontiers of science from space. Fundamental physics, basic knowledge about the behavior of matter and energy and gravity, really understanding the truth. When they say fundamental physics, it doesn't get more fundamental than the kind of work that we're doing with this cutting-edge laboratory flying on the space station. That zero-G environment gives us a whole new way of exploring fundamental physics. And you're going to hear tons more about that from people who are highly qualified to talk about it, both the scientists that are involved in it, and I'm thrilled that we have Eric Cornell, a Nobel Prize winner here, one of the real founders of this field, with us today. We've got Christine Koch, who has helped us with installing the update to the Cold Atom Lab, a great astronaut from the ISS. Christina, really great to have you here, as well as our whole JPL team and science team from around the country and hopefully around the world, everyone who has helped us get to this point. We also, Craig Kundrat from NASA headquarters here, who oversees the whole biological and physical research program for NASA. So we've got a cast of superstars here to talk with you about the extraordinary achievements of the Cold Atom Lab on ISS. And I think the best is yet to come. We're really just dipping our toe into this uncharted water of fundamental physics from space. There's so much more to do. And so as we celebrate where we've gotten to in this last 4 years, I really hope today we'll also talk about where we're headed. What's next? What is the next frontier of discovery as we continue to update the Cold Atom Lab on the space station? And you know, one of the other amazing things about this experiment is it's a great example of NASA's human spaceflight program working together with its science program to really advance the frontiers. We could not do this work without amazing astronauts on the ISS to help us run these experiments. It's you know, those of us who are lab rats like me, you know, we're in there sort of tweaking things all the time. And when your lab's in space, that's impossible to do without the assistance of our highly trained and very collaborative astronaut corps who support everything we're trying to do with science. So we're so grateful for that collaboration. We're grateful for the collaboration with headquarters, with international partners. We're working on the next phase of Cold Atom Lab with our partners in Germany. And the best is really yet to come. So I wish you a fabulous celebration of some truly mind-blowing science that you're going to hear about. Well, honestly, so I've been talking a lot in the last few weeks about extraordinary images from the James Webb Space Telescope, right? Those are pretty cool. And that's an amazing accomplishment. And I've been talking about how the instrument that we built here at JPL, MIRI, is really, really cold. It's operating at, 6.4 Kelvin right now. And you all are like, oh, my God, I'm hot. I need a fan. That's like way too hot for us, right? Pico-Kelvin above absolute zero. Like this, it's just mind-blowing, the science that's taking place here. And the only way to get this science done is on something like the ISS with something like the Cold Atom Lab. So extraordinary accomplishments to celebrate, very bright future ahead, and we just appreciate the students, all of our interns who are here, the PIs who are here, the engineers who helped bring this to life, the astronauts who've worked with us, and partners around the globe in making this happen. Enjoy this nerd fest that you are about to have on fundamental physics from space. And again, welcome to JPL. We're thrilled you're here. Thanks.
Thank you, Director Leshin. And as she said, let your nerd flag fly today. Now, our next speaker is responsible for providing strategic direction and overseeing the planning and execution of the two-pronged mission of pioneering scientific discovery and enabling human spaceflight exploration. He is the Biological and Physical Sciences Division Director in the Science Mission Directorate at NASA headquarters. Please welcome Dr. Craig Koendrat.
Thank you, Brian. It's a great pleasure to be here to celebrate 4 years of the Cold Atom Laboratory. As Brian just mentioned, in the Biological and Physical Sciences Division, we have a two-pronged mission of pioneering scientific discovery and enabling sustainable exploration. CAL is the exemplar of pioneering scientific discovery in BPS, Biological and Physical Sciences. Unlike our scientific brethren in the rest of the Science Mission Directorate, which typically study space or the Earth from space at very large scales typically, in BPS, we are experimentalists, and CAL is a great example of an experimental program that is capitalizing on the unique environment in low Earth orbit on the ISS, which is basically long-duration free fall, where atoms can be studied at ultra-cold temperatures in extremely weak potentials. And you'll hear a lot more about that in the subsequent talks. But at a top level, CAL has already had many firsts. Recently, the CAL project published on quantum bubbles. You'll hear a bit more about this later. And just last week at the ISS Research and Development Conference, Nathan Lundblad, representing the Bubble team and the JPL Ops team, accepted an award for the Physical Science Result of the Year award at that conference. Very noteworthy. CAL has created the first Bose-Einstein condensates in space, and has created the coldest place in space. And so CAL, as you'll hear more about later, has pioneered in many respects. But with pioneering, very often it comes difficulty. And I want to give a shout out to the broad number of people that have been involved in making CAL a success, starting with here at JPL, the hardware developers and operations team, the science team, the principal investigators and their teams coming together to solve many challenges in operating CAL, the ISS program in supporting operations and enabling up and down mass, and of course, as you'll hear later, our astronauts, and one in particular you'll hear from today. So pioneering isn't easy, and this group has done a fantastic job to be tenacious, patient, and show that fortitude to bring all these results. Having said that, we know that there's some really exciting results in future, because just recently CAL has demonstrated dual species Bose-Einstein condensates, you'll hear about that, and demonstrated atom interferometry. So you'll hear about these things, which are opening up a whole new lane of research for the coming years. And with that, I'd like to again emphasize my thanks to the broad CAL team on their perseverance and dedication, and to the great successes that we're able to celebrate here today. Thank you. And now let's hear more from John Callis.
Good morning. As mentioned, I'm John Callis. I'm the Program Manager for Fundamental Physics here at JPL. Let me also add my welcome to the CAL Science team and to all our distinguished guests here today. And also let me also acknowledge the great technological and scientific accomplishment of the CAL experiment. So I'd like to give a little scientific context to today's celebration. So let me start here. This is one of the recently released images from the James Webb Space Telescope. This is their first deep field survey. And what you can see in this image, which is no more than a grain of sand held at arm's length, are thousands of galaxies, a few stars, and the effects of gravity. These galaxies, if they are like our own Milky Way galaxy, consists of hundreds of billions of stars. And so by extrapolation of that grain of sand to the entirety of the sky, we can estimate that there's something of the order of 10 to the 22 stellar systems out there in the observable universe. This is an incredible domain of exploration. And this observable universe is beautifully described by two great theories of fundamental physics, the general theory of relativity, which tells us about gravity, and the standard model of particle physics, which is essentially quantum mechanics or quantum field theory. But as magnificent as these theories are in explaining what we see here, we are only seeing a tiny fraction of our universe. That's because more than 95% of our universe is dark, that only a tiny fraction is luminous. So this darkness is in two forms, what we call dark energy and dark matter. But we don't know what these are. Our standard model that I was just mentioning, which beautifully describes the observable universe, doesn't explain this. This is a gaping hole in our understanding. And further, our very existence is incompatible with the standard model because the universe is made up of only what we call baryonic matter and no antimatter. The standard model would explain that we should have equal amounts of each. And so why is this? And further, general relativity or theory of gravity, is it really the last word on things? Why have we been unable to unify gravity with the other forces of nature with this standard model? So these are significant shortcomings in our understanding of this vast universe. And again, we only observe a tiny fraction of it. So our great scientific vehicles of exploration, our giant accelerators on the ground, our magnificent observatories, have been unable to shed light on many of these great questions. So how can we answer these questions? Well, perhaps one way is to go into space. The microgravity environment of space creates an opportunity for us to create perhaps the most precise sensors possible. Cold atoms, free from the effects of gravity, become these ultra-precise, quiescent, tiny probes that we can use to explore these great scientific questions. So, okay, specifically, how would we go about investigating these questions? Well, what we are trying to do in the Fundamental Physics program is use a suite of exploration technologies. One is to use clocks. By putting optical clocks in space free from the effects of gravity, they become more precise. Clocks in space are more accurate than clocks here on the surface of the Earth. By having these clocks in space and having them operate so precisely, we can monitor their frequency or their tick and look for deviations that are due to changes in gravity or the presence of tiny unseen forces. We can also use the moon as a laboratory for exploration. By using new laser ranging techniques, we can make the moon a test mass and literally repeat the experiment that Galileo did from the Leaning Tower of Pisa and look and test the equivalence principle of gravity, which might shed light on many of these great questions. We can also create deep space quantum links, where we use quantum mechanics itself to look for deviations and our understanding of these scientific theories, perhaps revealing hidden variables or unseen new physics. Not directly to these questions, but also equally important, is we can use microgravity environments to explore dusty complex plasmas to reveal things about phase transitions and critical theories. But we can also put atom interferometers in space. This is where we take ultra-cold atoms and we use their quantum mechanical wave nature to create an interferometer, which becomes one of the most precise tools for measuring our physical universe. So Cal is one of those instruments that is pioneering this technique to explore these great physical questions and to reveal potentially new physics. And so today we are celebrating CAL, and I think this is a magnificent way to acknowledge our exploration into this world of fundamental physics.
Good morning. My name is Kamal Udriri, and I'm the Cold Atom Lab project manager. So I'm here to basically, I will be introducing our first keynote speaker, astronaut Christina Koch. But I would like to take a few minutes to basically also thank our team and tell you a little bit about CAL. So it's a little hard to do it in a couple of minutes, but since you're going to hear all the details from both our project scientists and also our Nobel laureate. So let me start by saying first, I will go over the presentations if you don't mind. Okay, so first we will hear from astronaut Christina Koch, and she will talk about mission space station science, followed by Jason Williams, who will talk about the science of CAL, or some of the accomplishments, and Professor Eric Cornell will talk about quantum science in space. So we're here today celebrating 4 years of quantum science in space because of tremendous determination and dedication by the people that actually proposed, designed, built, and now operating and using Cold Atom Lab. We're also here to celebrate CAL's firsts, and there are many, and so you heard some of them, but there is still so much that we can still do in the quantum world. So basically, we're not done yet. So this is 4 years in space, and we've been extended to operate until at least 2026. And this is made possible because of all the help and the support we get from also our crew office. So what is the Cold Atom Lab? It was launched to ISS on May 21st, 2018 on Cygnus from Wallops in Virginia, NASA's Wallops. And we took about a few months to perform what we call commissioning. And we started our science operations around this time, August 2018. So we've been operating in space since. So in a sense, if I want you to remember, so the Cold Atom Lab is a laboratory orbiting Earth, operated remotely from Earth, from here at JPL. The Cold Atom Lab is the size of like a mini refrigerator. So if you can see astronaut Christina Koch, she's facing the science instrument, which fits in four quadrant, and then we have all the power electronics and so on in a single locker. So in a sense, the Cold Atom Lab is the first quantum science laboratory in space that is remotely operated from Earth. In terms of cold, when we think about a cold place on Earth, we think of Antarctica, for example, right? With a temperature of, like in a winter night, of minus 83 degrees Celsius. Or if we think of the moon, the far side of the moon is about minus 173. But all this doesn't come close to the temperatures that we daily generate or achieve with the Cold Atom Lab. And even if we compare it to space, now I'm going to shift a little bit the unit. So space has an average of 3 Kelvin temperature, and with the Cold Atom Lab, as you will hear in a few minutes, we've been able to achieve 52 picokelvins. And most of our experiments use about 100 nanokelvins. So there is a huge difference, and that's why when you look up and you look at ISS, it's basically the coldest spot in space. So I want you to remember the 52 picokelvin done with the Cold Atom Lab. So what you're looking at here on the top left, that's a typical cold atom laboratory here on Earth. You see lasers, electronic for controlling, optics, the ultra vacuum. These types of experiments are considered the most complex tabletop experiments on Earth. And what you don't see here, actually, it usually requires multiple people to run this kind of experiments because they're really hard to keep running smoothly. And if I'm saying this because I've had a chance to talk to so many physicists and they acknowledge this. And the challenge we had, and this is almost like to scale, is basically take all this stuff and make it fit in a small box. On top of this, it had to be operated remotely. And some of these, challenges also involved how we would deal with the repairs. So in a sense, it took a lot of hard-working people, and especially I see around like students. So many disciplines, electrical engineers, mechanical systems, thermal. It takes many different disciplines to make a mission like CAL successful. And we've been, as you heard, operating in space for 4 years. And luckily, the idea of the design of this modular approach also has helped us a lot, and in a little bit of time. So what you see here, it's the same part of the instrument, of the science instrument. That's the science module, and that's where all the science happens. And at the heart of this science module, there is the physics package and this ultra-sensitive vacuum, as I mentioned, and we did it in collaboration with our partner, Colquanta. Played an important role also in the success of CAL. So you heard John quickly mention about the fact that why space. I mean, we can think of it like when you see astronauts floating, right? That's the same kind of idea what happens when we cool atoms. So when they float, we get to observe them at longer period of time. So basically, the Bose-Einstein condensate have been produced on Earth, and actually, the first person to ever do it is here with us, is Professor Eric Cornell on the ground, 1985. And the idea is, because of gravity, it limits the amount of time that we can observe this ultra-cold atom. So by going to space, it helps us to observe it at longer time. And also, this kind of sensors, just John talked about dark matter, dark energy. On top of this, there are some applications, especially we here at JPL, we're so involved in planetary science, so it can improve sensors for navigation and also, for gravity and understanding interior structures of planets. And additionally, it can even help us study Earth's climate. And, sorry. So what you're seeing, that's like a cloud of atoms. We usually use lasers to slow down the atoms, and then also we use magnetic traps to control them. And this combination of lasers and magnetic traps allows us to reach lower temperatures in microgravity compared to Earth. All right, so what you're looking here, and this is not something I'm going to go over because that's going to be like the focus of Professor Eric Cornell's talk, but this is just the Bose-Einstein condensate. So we'd like you to remember from this. First, Bose and Einstein thought about this almost 100 years ago, in 1920s. And they published a paper that if you can cool atoms to very ultra-cold temperatures, these particles start behaving like waves, and if you lower their temperature further, these waves combine or collapse in a single wave, and they become the Bose-Einstein condensate. And the idea, you can think of it like it's a different form of state of matter, right? Like we know liquids, gases, and solids and plasma. This is the fifth state of matter, is Bose-Einstein condensate. Why this is important? Because think of the Cold Atom Lab. Every day when our team shows up to the operations room, their idea or their primary objective is to make the machine or the Cold Atom Lab create this Bose-Einstein condensate, which almost like looking at quantum in a macroscopic level, and they use this Bose-Einstein condensate to do their science. So we're supporting about 5 science teams, and the idea is they expect us to produce this level of Bose-Einstein condensate, and they use this interesting matter, as I said, to do their experiment. And just because 5 teams are working on Cal right now, that doesn't mean that we can have many people use the same kind of fifth state of matter to create their own experiments in the future. And that sums up what I wanted to say quickly about Cal, and now I'm going to take a minute to introduce our distinguished guest, Christina Koch, but I think I just want to make sure, actually Christina Cook, right? That's how you prefer, yeah, okay. I'm a little struggling with the light, but okay. Christina holds a bachelor's degree in electrical engineering and physics and a master's degree in electrical engineering from Northern California State. Prior to becoming an astronaut, her career spanned 2 areas: remote scientific field engineering and space science instrument development, including her work at the NASA Goddard Space Flight Center Laboratory for High Energy Astrophysics, where she contributed to scientific instruments on several NASA space science missions. And actually, I found out that Juno was part of this NASA missions. In June 2013, Christina was selected as one of the 8 members of the 21st NASA astronaut class. In 2018, she was assigned to her first space flight, a long-duration mission on the International Space Station. She was a part of ISS expeditions 59, 60, and 61. She has conducted 6 spacewalks, including the first 3 all-women spacewalks, totaling 42 hours and 15 minutes. Christina has also set a record for the longest single space flight by a woman, with a total of 328 days in space. Throughout her career, she has been involved in the technical instructing volunteers, tutoring, and educational outreach. She also enjoys a wide range of activities, including backpacking, rock climbing, paddling, surfing, running, yoga, community service, photography, which we've seen some of your amazing photographs, and travel. So, please, let's welcome Christina Koch. But before, we have a little surprise for her. And I want to just give you a little perspective, because you've heard about the upgrade to the CAL. Because the Cold Atom Lab, when it was launched, it did not include atom interferometry, which is, like John mentioned, it's a critical part of our science tools to help us study the universe. And we had to struggle. Do we want to bring back the instrument and do the upgrade here? And that was like, some people highly recommend that we do this. Or we turn and rely and put our faith in the hand of astronauts and see if it can work. But we were told there was going to be 50% chance. Sorry. But the problem, had we brought it back, we would be down for at least 2 years on the ground. Our stars lined up, lucky stars, so to speak, and we were so lucky to have astronaut Christina Koch, who, when we looked at all the work she had done, we knew that we had a good chance, and we watched her. We worked, from the ground, and she did an amazing job, and once again, as I said, we had there is no chance for any errors or anything, because it's a science instrument, which means it's a single string, like there is no redundancy, and she did it in a record time. And because of her amazing work, we would like to take a moment on behalf of JPL to thank her for all her exceptional work. And I'm going to read the plaque, and I will ask our Dr. Keyur Patel, Director for Astronomy and Physics, to hand her this plaque. But I just want to go ahead and read it, if you allow me. Presented to astronaut Christina Koch for your exceptional support to enable the upgrade of the Cold Atom Lab with atom interferometry in space, from your friends at NASA's Jet Propulsion Laboratory. Thank you. Okay, sorry. So let me take a picture.
Thank you, Kamal. This is just such an honor and such a surprise. I feel like I was the one that my lucky stars aligned so that I could be a part of Cold Atom Lab. And actually, what I'm going to talk about today is that whole story. So I won't go into it now, but it is such an honor to be here with you all, to share this stage with these amazing people, and just to be in your presence. I definitely let my nerd flag fly often, and JPL has always been a place that was kind of a beacon for me in that regard. And it's just, anytime I can get here is a wonderful day, and anytime I can work with the teams here is even better. So oftentimes when I speak, I just talk about my mission, my journey, how I got to space. And today it's a little bit more targeted. I'm going to talk about how I became the Space Cold Atom Lab repair guy. That was the real journey that was going on, it turns out, my entire career, and I'm going to show you why. So I started straight out of college at Goddard Space Flight Center in a lab that did superconducting sensors for astrophysics. And I had to learn how to work with liquid helium and liquid nitrogen. And so this was back in the day when I thought 4 Kelvin was cold, maybe 6.3 microkelvin was cold. That obviously all changed throughout my journey. And actually it started even before this, because when I was in grad school, I actually got to do all of those wave equations for Bose-Einstein condensates. And I remember thinking at that time, wow, I'm never going to use this. But I have to report that after having worked on Cold Atom Lab, I still have never used it. But I at least knew how to spell BECs by then because I had done that work in grad school. But it turns out after working in a laboratory on Earth that did a lot of cryogenics, I needed to then be at the coldest place on Earth. So I worked at the South Pole Station in Antarctica for a while. This is where Science on the Frontiers really first started energizing what would become my career path. And I was actually the cryogenics technician of the South Pole Station. Our motto was, when the South Pole just isn't cold enough, come to us. And we did have a liquid helium thing, again, to enable the astrophysics that happens there. I worked in some missions at the Applied Physics Lab, always with the space science and instrumentation in mind, and oftentimes also in very cold places. And that's when I found myself here, having been selected as a very lucky member of the 2013 astronaut class. And soon after, we got started into our what we call astronaut candidate training. So this was where I learned a whole lot of different career paths and things that I would have to do to eventually be the Cold Atom Lab repair guy, including how to fly a supersonic jet, how to do spacewalking, which we learn in our gigantic pool facility called the Neutral Buoyancy Lab that has an entire mock-up of the space station underwater so that we can practice this work. And even during our time learning how to become astronauts, my astronaut class got to visit JPL, so that was a really exciting time. We saw the Mars Yard. We got to do the fundamental physics tour as well. And eventually I got my flight assignment, and that's when we go into flight-specific training. This is us training on some of the other science that we do on board the space station. And this is actually the first time I learned about Cold Atom Lab. And I remember thinking, wow, if I get to work on that when I'm up there, that would be really cool. Think of everything I've done. This is the obvious next step for me, to work as part of an experiment that claims and is the coldest spot in the universe. So that was an exciting possibility. But I was told that no one ever really works on that. That's something that astronauts don't actually get to interact with, because as you've learned, the experts usually can run it directly from the ground. And so I knew that I would have to get really lucky and have an opportunity for an upgrade or something like that. Kept on training. I was an astronaut that launched on the Soyuz rocket out of Kazakhstan. It's a Russian rocket, so part of my training, and actually quite a bit of it, was in Russia. And then came this day. The actual launch day, and 8 minutes later, finding yourself in microgravity when that third stage cuts off and you float a little bit out of your seat and you know you are one step closer to Cold Atom Lab. The spacecraft obviously becomes a free flyer for just a little while. We end up at the space station about 6 hours after launch, if you can believe it. It's pretty quick. And that hatch here is what actually docks, and it's the hatch that we open to enter the space station and meet our friends. So life on board is a lot of, it's a combination of a lot of things. Obviously, we all know that the main mission of the space station is to be a national lab that does the science that can only be done in that space environment. But to keep it running, that involves a lot of maintenance, most of which is on, racks that do all of our life support systems, all of our avionics. Sometimes we get lucky, and for an electrical engineer, we get to do some of the board level work and repair. This is one example of those times. And then other things, when visiting cargo vehicles come, we actually operate the robotic arm to bring them aboard and to make sure that we can get those supplies, some of which are the new science experiments. And of course, spacewalking. So this is Jessica Meir and I, who we were honored to be the two astronauts that got to do the first ever spacewalk that was conducted by two women, first all-female spacewalk, and we got to go out and do that 3 times together. And that is truly just one of the gems for any astronaut, being able to enable the space, the science to continue on the space station by upgrading and repairing the outside of the space station. We also love the international collaborative aspect of the space station. It's one, in my opinion, of its loftiest goals and its loftiest achievements. And this is me working with my actual Russian commander, Alexei Ovchinin, preparing for one of his spacewalks that I got to help with. And now a little bit about the science. So this is a video that we put together as a compilation of a lot of the different science, and I'm going to narrate it. The actual video has some music, so bear with me. One of the life sciences experiments that we do is the plant work, and in this video you hear me talking back and forth with the folks on the ground about how much water to actually put in each of the plants. And one of my favorite things about working in space is you feel like you have your lab partner on the ground, and you really have a great relationship with that person that you're working with. I got to talk to Jim Kellogg from this Cold Atom Lab for days working on it together, and you really you get to feel like you are a part of that team. Jessica and I, again, working on our plant lab. This is an experiment with tissue chips, so actually doing some biological experiments on a chip that's able to represent some of the mechanics of our biological systems that we're studying. And of course, the Cold Atom Lab, when it got there, I made my buddy get out the camera and take pictures of me, because at that point, I didn't even know if I was going to get to work on it or not. I was just excited to see the label on the outside of a box. And this is a really neat experiment where we were actually doing biological printing. So experiment that, again, utilizes that microgravity environment to build up 3D models of what we hope one day could be actual organs. And there I am getting started on Cold Atom Lab one day. Combustion experiments, flame sperm spherical in space, everything you can imagine. And I think the last sequence here, this is actually a great sequence where it shows someone had noticed from the ground with the over-the-shoulder video that I had forgot to cap one of their cell cultures. And it was just, again, another example of how fun it is to have that teamwork with people on the ground. Automated tech demonstration experiments, and a lot of how cellular organisms react to the microgravity environment. A lot of people ask me, what kind of science do you do on ISS? And I say, it's not one kind, it's just the kind that you can't do anywhere else. And anything that qualifies, we do it up there. So since we're in the nest and this is a small group, I thought I'd share that this picture that is one that I love so much actually was not as easy to take as it might appear. It's not very easy to pose for pictures in microgravity, especially when you're carrying a multi-pound object with you. And so part of this, it didn't actually go as easily as it appeared in that other picture, but we had fun. And working on the experiment, whether that be in front of it or from the ceiling. And I was not working this fast. I appreciate Kamal mentioning that I apparently did work quickly. This is a sped up video of some things, and actually I need to go back because I missed the one thing I wanted to show you. So just going to narrate a little bit like the real life side of what's going on here. So this thing over here is actually our exercise bike, and you'll see there's a hand that pops on. Someone was actually exercising on the exercise bike right next to me while I was doing a lot of this work. I put this one up. I hope I'm not causing anyone any consternation in the Cold Atom Lab team, because I can only imagine what was going through their mind when they saw some stranger with their hands inside of their very, very delicate instrument and working in the minutia. But they did such an awesome job of training me. They actually scheduled time for me to learn how to use all of these new tools with lasers and the fiber optics. There I am. So this, you notice I went off camera for a second while I'm talking to Jim, and that was the space equivalent of being on mute, because I tried to talk to him with our audio unit not turned on there. So that just shows you that I started that before Zoom calls were cool. I just did a little day in the life. I really enjoyed going back through these videos to prepare for today. And I wanted to also thank you all. I don't know if you heard about this. Was the first all-female replacement of a science module on a Cold Atom Lab that was also done during my mission. And obviously, just a joke. But there was an opportunity that I got to work with Jessica on this, so that's always fun. But we don't only work on board the space station. Yes, we have some time off. One of my favorite things to do in my time off was to be in the cupola window looking down on Earth and taking pictures, and including one of you all. Oh, the circle didn't show up, but there was a circle around you guys, or did it show up? Oh, okay, thank you. But my favorite night photography, I obviously really enjoy this, and looking down on those cold regions that have the northern lights and southern lights from up there was really special for me. This is my video. This is just us having a little bit of fun. That's me and Nick Hague, and you can see Drew Morgan actually exercising in the background. But this is, in my mind, what's happening inside Cold Atom Lab. There's a blob, and thanks to being in space, we can maintain that blob a little longer than we can maintain blobs on Earth. And, you know, there's, like we talk about, no asymmetric interaction with boundary conditions and a longer lifetime. So I wanted to offer that up as a little explanation. Of course, no recreational time is complete without dinner with your buddies, and that was another fun way that we bonded as a crew. Of course, all good things must come to an end, and eventually after 328 days, the day that I did the upgrade on Cal was like day 320, believe it or not. I slipped it right in before I got to come home. And landing in a field in Kazakhstan, getting extracted from the spacecraft, and actually 24 hours later being back in Houston. This is me thinking, I did it. I worked on the Cold Atom Lab in space. And of course, we are at a really exciting time now. What's next for astronauts? And this is where the partnership between the human spaceflight and Johnson Space Center and what you all do here at JPL is so important, because we are going back to the moon. We're going to be partnering the robotics and the humans together. Obviously, can do more than what any of us can do alone. And I think Cold Atom Labs collaboration showed that, as well as the future work that we're going to do. So we can't wait at Johnson Space Center to keep working with you all as you all explore other bodies, and we're a part of it. Thank you.
Thank you, Christina. Just I want to say something. Yeah, so the science module that you replaced, we brought it back to Earth, and it has found a home at the Smithsonian Museum. So it will be given to them soon. So we just want to make this announcement and let you know. So thank you so much.
Okay, thank you. I'm Jason Williams. I am the project scientist for the Cold Atom Lab, and I have the distinction to introduce Professor Nobel laureate Eric Cornell in just a few minutes, but I wanted to take a minute to talk to you about the science that we and the distinguished and very helpful PI team have been doing. And so Cold Atom Lab has been operating for 4 years, and it has been an exciting 4 years, I'll tell you that. I see a lot of some of the members of the Cold Atom Lab team that are here. It's been a big effort, a fulfilling effort for many of us, and not only scientists, engineers, operations team, students. It's been, I've never worked with a greater group of people. And astronaut Christina Koch was talking about doing some of the work on Cold Atom Lab, replacing it. We got the chance to watch this from the ground. It was exciting. Also one of the scariest moments of my life. But she did an amazing job because, as you'll see, we've gotten some really great science out. So as Kamal had mentioned, we've operated for 4 years. We also have collected tens of thousands of experimental runs for the PI teams. And so this is absolutely the most Bose-Einstein condensates that have been produced in Earth. This has actually been demonstrated as the first multi-user facility for quantum gas research in space, and it has really fulfilled its promise, going above and beyond the initial mission lifetime. We achieve Bose-Einstein condensates in space. In fact, we produce them every day as part of our startup. And we can now not only do experiments with rubidium, so a single atomic species, but we can produce dual atomic species Bose-Einstein condensates, rubidium and potassium. These are very different atomic species. They have different masses, completely different properties, and we can also produce those at the same time. and manipulate them in space, allow them to interact, and flushes out another very large body of physics that has been opened up for the first time in space, studying interacting now ultra-cold quantum gases. We've also, as part of the commissioning, seen atoms just floating in space in free fall for seconds timescales, which is extremely long time for us. And as also Kamal had mentioned, we've achieved unprecedented cooling to sub-nanokelvin temperatures, even down to the 52 picokelvin regime. So this picture I really enjoy of astronauts finding a Bose-Einstein condensate in space and observing its properties. In many ways, that's what we're doing, though. We're releasing these atoms in space. We actually take pictures of them as part of our data return, and we're seeing what they do. We see their unique properties. Okay, so I wanted to take a few minutes to talk about the PI teams, because they're really the heart of what we're doing in Cold Atom Lab. There were 5 flight PI teams that were chosen for the initial Cal NRA, and these are really pathfinders. No one's ever done experiments like these 5 PIs have done before. And so, for example, Nathan Lundblad has been doing some experiments observing ultra-cold gases in bubble geometries in space. And so how does a quantum gas with wave-like nature perform when it's in this unique topology of a bubble or a shell? These are experiments that are beginning and have been progressing well for Nathan Lundblad. The team by Nick Bigelow, he leads a consortium that includes Nobel laureates Wolfgang Ketterle and Bill Phillips, and his team is really exploring, okay, I have 2 atomic species. If I perform atom interferometry on it, which I will explain a little bit more in a few minutes, this can be a very precise sensor for gravity. So how can we take Cal where it is, mature the technology so that someday we can perform dual species atom interferometry and try to test some of Einstein's theories, such as the universality of free fall, or do these quantum objects fall the same in gravity? We know they do, but to what level do they really fall at the same rates in gravity? And the group of Eric Cornell, you'll hear a little bit of his talk of what he's doing, but his group is, along with Peter Ingles, is studying the quantum 3-body problem, which is a very difficult problem to study, but it has universal properties that can be extended to other systems. Sort of analogous to Feynman's quantum simulator. We can take atoms as quantum systems. We can simulate their properties. Now, how does that extend to the rest of the quantum world, perhaps like nuclei and molecules and other things that are much, much more difficult to study? Cass Sackett's group is studying adiabatic cooling in space. A lot of his initial efforts are, how cold can we make things? If you have space, have a uniform environment, and you relax the confinement and so-called adiabatic cooling, but make extremely weak traps, your atoms are going to get really cold, and really trying to push the limits of how well we can prepare ultra-cold gases in space. And then my team is studying Feshbach molecules, these unique type of molecules with quantum gases. It's sort of a form of quantum chemistry. How can we form these molecules, and how can these be used as a very precise source for precision measurement in the future? And so this is these are initial experiments that have popped up. These are all are space enabled, and we've been getting some very impressive results. To zoom in a bit more, since the upgrade by Astronaut Coke, this brought to us the capability for atom interferometry. And atom interferometry says, okay, we know that atoms are waves. We've known that since the 1920s. It's one of the basics of quantum mechanics. Using some more recent technologies that have been developed to use laser pulses, you can use a laser pulse and split 2 atom waves apart and allow it to recombine and interfere with itself. And you make an atom interferometer out of matter waves. This is a technology that is developed on Earth. It has a lot of promise in space, because in space you don't need to drop your atoms and allow them to drop a long distance. You release them and your atoms float in free fall. And we have some very cutting edge results. We've demonstrated for the first time a dual species atom interferometer where single laser pulse creates two atom interferometers, and we see how gravity at a very low level acts on potassium and rubidium. And this is a basis for experiments that are going on, but first time that this has been demonstrated in space. And this, as I mentioned, will form the basis of eventually maturing the technology to look for violations of the equivalence principle, and this is one of the great tools that has promise for searching for new physics in the future. So with that, I would like to introduce Professor and Nobel laureate Eric Cornell. Thank you. So Eric is a fellow of NIST and JILA, a adjunct professor at the University of Colorado in Boulder. He has a very long resume. I had a hard time distilling it down, but his current research includes searches for the permanent electric dipole moment, some studies of strongly interacting gases, and the few body problem. He's one of the first PIs on Cal, and he also has a very distinguished awards record. Received the Presidential Early Career Award, Robbie Prize, member of the National Academies of Science, and in 2001 he received the Nobel Prize along with Wolfgang Ketterle and Carl Weinman for first demonstration of Bose-Einstein condensation in a dilute gas. So we wanted to present this award to him, and so I will again allow Keyur to present it, but this is in recognition of Eric's leadership. Thank you. In recognition of his leadership and support of the advance of cold atom technologies for space. So thank you, Eric.
And thank you, Jason. It's always really a lot of fun for me to come to JPL. This is the 4th anniversary of Cal in Space, but I've been involved one way or another in the program for 8 years, going on a decade, and it's been so exciting for me. If I had only a single gripe, it would be that somehow at Cal events I often end up speaking after Jason and Christina, and I always feel a little bit not quite as polished, but I'm going to work on it. I'm here to talk about, people have alluded before to quantum in space, and that's the topic of my talk today. Before we can talk about quantum in space, I want to talk about ultra cold in space, and sort of tie that into a word we've already heard before, which is Bose-Einstein condensation in space. I'll probably forget, in giving a sort of popular level lecture, when tries not to use acronyms, I'll probably forget and call it BEC, but you're not really working at NASA or JPL if you don't throw around a lot of PLAs, and so I've got into the habit myself. BEC, Bose-Einstein condensation. So I'm going to start with the cold. And just to put things in context, scientists, engineers, we measure temperatures in absolute units. So not so much 81 Fahrenheit, but something close to 300 degrees above absolute zero. What we would call minus 460 Fahrenheit is what we would call absolute zero, 0 degrees Kelvin. You can't ever get to 0 degrees Kelvin, but as we'll see, you can get awfully close. An important line which you can maybe just barely see in the auditorium here is just barely above that purple line is the temperature of deep space, 3 Kelvin, which is, people have already alluded to, cold, but not really. We get a whole lot colder. In fact, the next slide we're going to expand out between that 0 and 3 and draw the analogy. The 3 degree temperature of deep space is to Mount Everest as say the thickness of 100 nanokelvin, the typical temperature of Bose-Einstein condensation, is to the thickness of a pencil lead, say a millimeter. So we're going down whatever this works out to here, 7, 8 orders of magnitude down in temperature from what already people usually think of as a very cold place. Why so cold? What's the relevance of cold, and how does that connect us back to quantum mechanics? And I will say, it's a little bit of a spoiler alert, this 100 nanokelvin, which I'm making such a big deal, 100 billionths of a degree above absolute zero, Cal gets a whole lot colder than that. I don't have time to talk about how we get so very, very cold. People have already alluded to lasers, and indeed, we use the pressure of lasers, of photons bouncing off of atoms. Think of throwing ping pong balls at bowling balls, and if you throw enough ping pong balls at bowling balls, you could slow down a bowling ball if it happened to be rolling towards you. Going slower means being colder. That's laser cooling. And then laser cooling is part of it, and magnetic trapping is part of it too. Both on Earth and in space, we have strong magnetic fields that keep the atoms together in a little blob, and we let the hottest atoms fall out of the edges, much like a cup of hot coffee lets the steam flow out. Get the cup of hot coffee, you see the steam coming out. That represents the hottest of the coffee molecules making a break for it and taking away with them more than their fair share of energy, cooling the remaining coffee off. Evaporative cooling and a magnetic trap. These two techniques allow us to get the Bose-Einstein condensation. Here's a picture from really a long, long time ago, early pictures of Bose-Einstein condensation. And you'll see these false color images multiple times. You already have seen them. These just represent density plots. Basically, you turn off the magnetic trap, you let the atoms fly apart for a little while, and if they're going relatively fast, as they would be at 400 nanokelvin, they spread out in both directions. And when we take a picture, we turn these shadow images into these mountain-like pictures. If they're quite a bit colder, say 50 nanokelvin, then we see this single shark fin, dorsal fin, which is the Bose-Einstein condensate. It's a single wave representing all the atoms participating in the Bose-Einstein condensation. Here we're somewhere in between. Imagine that your ice tray is only a little bit frozen. You've got some ice and some water, some condensate and some regular atoms. This is the group that did this, Lovies, 30-some years ago. These people all went to Stockholm with us for the Nobel celebrations. I mentioned in particular Debbie Jin, who was one of the very first Cal PIs and unfortunately is no longer with us, died tragically young. What is this connection between very cold and between quantum? And what is quantum to begin with? Some of you, it's been a little while since you took your first course in quantum mechanics, and so we'll just review it here in about a minute. Atoms, like everything else, you can think of them as two ways. Either the classical way, like pool balls, bouncing off each other and maybe falling into a pocket, or like little quantum waves. As things get colder, they get wavier. What is that about? Why is making things get colder make them wavier? And really it comes back to, if you don't know anything about quantum mechanics, but you've just read a Scientific American article, you might have heard of the Heisenberg's uncertainty principle. You can't simultaneously know where something is and how fast it's going. Well, as you get colder and colder, you know how fast it's going, because colder and colder corresponds to moving slower and slower. So you can say, on average, the atoms are not moving at all, and I can say that with more and more precision as I make the atoms colder and colder. Their velocity is closer and closer to zero. Heisenberg says, sorry, if you know that very well, how fast something is going, you can't know where it is very well. And so these things look more and more like fuzzy balls. It's basically a wave-like object, and it's a result of the uncertainty principle. And as you get really, really cold, then waviness triumphs, and you get Bose-Einstein condensation. Here in Southern California, we would call it the ultimate wave. And how are they like waves? A beautiful experiment done by another Cal PI, Wolfgang Ketterle. He took, it pains me to say this because for many years he and I were like arch competitors, but these days we're kind of pals. He did this beautiful experiment. He took two condensates in sort of two separate little magnetic wells. He let them overflow with each other, and where they overflowed, he saw these stripes. Basically, these stripes are destructive interference between atoms. We think of waves like you see ocean waves, patterns of ocean waves. They can interfere constructively or destructively. True for light. You can get lasers interfering with each other, and you get these interference fringes. I find it still strange to imagine you can take atoms plus atoms, add them together, and get these sort of white stripes which correspond to like no atoms. Basically, one set of atoms cancels out the other atoms. and this is interference. A common thing in things which are waves, and now we can see very directly in these pictures that atoms are waves, these so-called fringes, these interference patterns, are extremely sensitive. And they are sensitive to things like acceleration and exotic new physics. There's a proposal out to use things like this to detect exotic new physics, including the gravity coming from things you can't otherwise see. Where do we hear about that? Dark matter, right? So these are projects for the future, and in some sense, Cal is a pathfinder for these kind of ideas. All these ideas will work better in zero gravity. If we could replicate this whole project of making Bose-Einstein condensation in space, they would just hang there, and we could get much colder without being bugged by whatever it is we are keeping the slow-moving atoms from just falling, which is what happens here on Earth. What puts the cold at the cold atom laboratory? Is it because space is cold? No, we've just heard space is honestly not that cold. 3 degrees Kelvin, come on. On Earth, we have to hold these things in these magnetic bowls. And I mentioned 5 nanokelvin, which is about as cold as this is already a very, very cold temperature on Earth, not even routinely observed. We learned in high school physics that if you take a gas and you expand it, it gets colder, right? Ideal gas law, all that kind of stuff. So we're holding these things in a magnetic bowl. Easiest thing in the world for a magnetic bowl is to turn down the electric current going in the coils. The magnetic fields get weaker. The bowl goes from a deep bowl, like say like a tea mug, into a shallow, like a tea saucer. And you do that gradually, the atoms expand and they should get colder, just like, PV equals NKT. The volume gets bigger, it should get colder. But so why don't we just do that? And the problem is, at least here on Earth, is that the bowl doesn't look like that. It doesn't look like a shallow bowl. It looks like a shallow bowl tilted on a side. This is gravity. The atoms will slide on out and they'll fall out screaming to their infinite peril, and that will be that. How does this connect with gravity? Well, I think Christina would be the first to tell you that in space, no one can hear you scream, so the screaming won't. No, that's not actually the reason. It's actually because there's effectively no gravity, basically, in space. So atoms don't fall out of the trap. We can basically do this adiabatic expansion and get down into temperatures that start with a P instead of with N. P stands for pretty darn cold. So why go to the trouble? Detecting gravitational waves, studying the equivalence principle, precision orology, which is a fancy name for really good clocks, dark matter. Cal will help develop all of these relevant technologies. It's a step in all these directions. We've already seen pictures behind. You can't see it, but behind these folks there are 2 optical tables. Think of them as large picnic tables full of stuff. Here's actually a more modern picture. Shin was one of the grad students supported by Cal, and so was Vandy here. More picnic tables, more stuff. When I first heard about Cal, they said, we're going to take all this stuff, we're going to squeeze it all down, we're going to put a box, and we're going to send it up into space where no one can mess with it for years and years, and we'll make Bose-Einstein condensation there. And I said, yeah, right. I don't think so. It's really, really hard, folks. It's not something you can just But to my astonishment, honestly, I was reluctant to get involved in the project because I thought there was no way in heck this is ever going to work, but it did, which is really pretty freaking amazing. Congratulations, Cal folks. That's astonishing. Can we just have a round of applause? That was an amazing thing to do. And we've heard a little bit about it. At the heart is a chip which was made by a company owned by my pal here, Dana Anderson here. The chip's about 1 inch on a side. I think here at NASA we say 2.54 centimeters, give or take. And it's got little wires that make the magnetic fields for the traps. That in turn goes into sort of a scientific environment about the size of a loaf of bread. That thing goes into, I always think of this as the dorm fridge. Maybe it's more like a hotel fridge. It's about the size of a dorm fridge. I still remember my college days when people had dorm fridges. And then that whole thing gets sent up into the International Space Station, and it's thanks to generous funding, a home in space, people to design and build this amazing thing. The original truly quantum mechanics who put the thing up on the rack and changed the oil or whatever it is that needs to happen. I can't imagine doing that in space. But yes, turns out, as we've heard, it's possible to keep the thing running for the Cold Atom Laboratory. We've seen some of these pictures already. Again, these pictures are not taken in space, but again, basically they turn off the cloud, they turn off the magnetic trap, the atoms just kind of hang there, and they gradually expand because they're not exactly at zero temperature. And after they're expanded for some time, they take a picture, and you see this is a representation of the density of the cloud, and it's getting, as it's heading towards Bose-Einstein condensate, it gets smaller and smaller and smaller, and then suddenly this spike shows up. And those spikes, like that spike right there, is thousands of atoms all doing exactly the same way. Think of it as like strands of hair in a giant Reagan-esque pompadour, something like that. And then finally you have a pure condensate. Other amazing things. So this is, sort of the starting point for many experiments that we've heard about. We heard from Kamal and from Jason, the exciting experiments, which I can't really go too much into, but I will mention that, here are some places where the cloud is just kind of hanging there, heading out towards a second. If you sort of characterize, this is like longer and longer time hanging there in space, you can see the cloud is getting, maybe a little bit bigger. You can sort of divide that increase in size by that amount of time and get a velocity. Call that a v, take 1/2 mv squared and call that a kinetic energy, divide it by the Boltzmann constant and call that a temperature, and you don't get nanokelvin anymore, you get picokelvin. Here's the scale I was showing before. Typical temperatures on Earth, order of 100 nanokelvin, 100 billionths of a degree above absolute zero. For people who speak metric, pico is to nano as micro is to milli or whatever. It's 1,000 times smaller. These are extraordinarily low temperatures, and made possible by being in space. People have already alluded to this ability to make condensates of two different species. They appear on one side of the screen or the other, but I want to emphasize they're actually sitting right on top of each other. Why would you want to do that? It turns out that when you're doing interferometric studies, for instance, of how atoms fall under gravity, there are a lot of possible, these are precision measurements, there's a lot of possible sources for error when you make precision measurements. You'd like to cancel out those sources of error, and the way to do that is by doing a differential measurement. You measure something simultaneously exactly overlapping with one species and with the other species, and most of the errors are common mode and subtract out, and the physics you want to extract from that lies in the difference. And then I can't stop without mentioning the experiment I myself am working on with my friends, my colleagues who are here, Marion and Peter, in which we're trying to create molecules, 3-atom molecules that are about the size of an E. coli atom. So that's like the loosest, tiniest, fluffiest atom molecule you've ever seen, held together by purely quantum mechanical forces. We're not quite there, but soon, I hope. At that point, I'm going to stop and thank you for your attention.
So, folks, we are now going to start opening it up for Q&A, but as they work their way over to their chairs over there, I want to give a big round of applause and a thank you for all of our speakers coming from far and wide to be here and talk about this amazing mission. So one big round of applause again for everyone. Our first question we're actually going to take from online. If you're in-house, you can step up to the microphone, so we'll get an online question first. We're going to go for probably the next 12, 13 minutes. If we don't get to your question, we do apologize for that. But a question from YouTube is asked, how has Cal helped us in our daily life? And I guess which one wants to take this one?
I'll take a crack at it. I feel like so far not so much, to be fair. But if the history of technology tells us anything, it's that the future lies in the direction of the very, very small. And our daily lives are improved by so many things which are involved, whether they're medical devices, whether they're electronics, whether they're computers, whether it's communication, which are based on these tiny little chips. As they get smaller and smaller, the rules of classical physics no longer apply and quantum mechanics take over. If you want to continue along this trajectory towards making the useful things that we want to buy and have in our house, we need to have a deeper, more gut-level understanding of quantum mechanics. And there's nothing more gut level than just being able to see a picture of quantum mechanics happening. So there's a sense in which these kind of studies represent a sort of, I don't want to call it a playground, but basically a working laboratory to understand this physics which sort of enables so much of the technology that underlies commerce and industry and household products.
Very cool. We'll go to another question from online. It's Marina on YouTube asks, can the Cold Atom Lab reconcile and unite quantum physics and relativity theory?
Yeah, I guess I should take that one. All of these technologies are relatively new, I should say, especially the promise that we're going to use these cold atoms in order to make very impactful statements about fundamental physics. It's not expected that the Cold Atom Lab in its current state will measure equivalence principle to 18-digit points or make some definitive statements about string theory or something like that. But it is a necessary first step and a large leap, I would say, to get us there. This is a technology pathfinder that has, to me, surpassed what the technology we were trying to pathfind and is now actually has dual species atom interferometry. Some of our PIs are working on it to actually do some preliminary tests of, say, the equivalence principle and see if it's possible. And from there, we have the knowledge now. We have that basis to build defined facilities that will be able to go in and really probe where we need to and understand and make some definitive statements.
So I would like to add, if we think of the Mars programs, like recently, I mean, we've landed 2 huge rovers, Curiosity and Perseverance. They're like over 960 kilograms. Well, we didn't just do it just on the first go. We had to send like Sojourner and learn from that. Then we went to Mars exploration rovers, and John can tell you. And then we learned and we built on this knowledge before we could land something that big. So I feel like the same thing with the Cold Atom Lab. It's pathfinder and the ability to be able to extract like two separate atoms or cloud of atoms like potassium and rubidium, and potassium is lighter than rubidium, and to be able to control and release them at the right time and be able to observe which one hits the platform first. That's a huge leap that we couldn't have done 5 years ago. So anyway, thanks. I just want to add this.
Fantastic. We actually have a question in the house right now, over here on the right side.
Hello. I was wondering, how can you use the Cold Atom Lab to understand or detect dark matter? You guys mentioned that it was like related to that, but how does that work?
Okay, yeah, I can take a first crack at it, and I'm happy for anybody else to jump into that, because this is really a branch of research that has been a pleasant surprise that has cropped up over the last decade or so, I should say. So dark matter emerges as subtle forces in our universe that we don't understand. And these are, there's been a lot of search over the last decades for what is the essence of dark matter. Could it be some particle that interacts with matter but we can't see? There is a class of dark matter that is ultralight. And so the idea that there are some very light particles, but enough of them that they're pervasive in our universe. And the influence of these ultralight particles might give subtle forces on quantum gases that could be perceptible. And so we could actually have a complementary new type of measurement that no other apparatus could possibly be used, or could possibly see this unique class of dark matter that is feasible, that could explain the unknown nature of strange forces in our universe that don't yet have an explanation.
Thanks.
Very cool. We have another question from Facebook this time. This is really focused on atoms. Is it possible to focus on molecules? Is it possible to focus on even more specific parts from this point, or is atoms kind of where we want to be with this? Yeah, Eric.
I could jump in here. May have heard, like, people haven't talked about it, but words have appeared on the slides like Feshbach and Efimov, which sound, just like exotic names, but in fact they refer really to molecules. Feshbach resonances are what happens when you take two atoms and you adjust the magnetic field and they stick together to form molecules. And these are projects which are very much ongoing. Soon, I think they'll be making molecules of, in this case, rubidium and potassium stuck together. We're working on trying to make 3 potassium atoms stuck together into a 3-atom molecule. And these are molecules which no chemist would recognize if you wrote them down on a chemistry exam in high school. It would be marked wrong. This is not a molecule. It doesn't obey any of the rules. But that's sort of what makes them fun. Is these are molecules that violate most of the chemistry rules just because they're so lightly bound. They're sort of like little balls of fluff, and they are sort of purely quantum mechanical objects.
Fantastic. We do have another question here inside the house as well. Wearing a great Mars shirt.
Hi, my name is Amy, and I'm an engineer on the mission ops for Mars 2020. And I was wondering, how did you figure out what you're most passionate about? And do you have any advice for navigating your career, especially for any students in the room?
I think everybody can take a crack at this one. Let's start with Christina.
Since you guys took the other hard ones, I'll take a crack. Great question. When I found myself at the many, many crossroads that you find yourself at in a career or in school, choosing a school, choosing a major, choosing what to do after school, choosing whether to take time off, I had that same question. How do you know the right path? How do you know what you're truly passionate about and what's going to lead you to not only flourish the most and get the most rewarding life that you can have, but to give the most back to the world? And one of the things I would always do is go back to what I imagined for myself. There's a quote, I think it's a Thoreau quote, live the life you imagined. And that is actually something that I think about. I think about when I was 8, what did I picture myself doing when I would grow up? And I actually would remember those memories and try to think about how I could create that life. And I really did see myself being a space science nerd, and even though I grew up in a small town in North Carolina, and I would follow that path. Another thing that I say is do what scares you. And what I mean by that is don't take unnecessary risk or anything like that, but think about the things that intrigue you, but that you feel like are maybe outside of your grasp. And that's the direction you actually have to go in, not away from. It turns out that can tell you what interests you and also where you're going to get the most reward out of, because it's probably challenging, and that's why it's a little scary. And when you do it, you actually see what you're capable of, and you probably have pushed yourself to give more back to the world. So those are some of my guiding lights.
Yeah, thank you, Christine. The only thing I would like to add, just basically what you just said, summarize it in the fact that when you reach outside your comfort zone, that's when you learn, and that's really what you are kind of conveying. And Cold Atom Lab is one example, because I think, you heard even from Eric, like he had doubts, and it's good to have doubts, because then you set some criteria that you have to convince the right people that you have the right plan. And so I think many of these missions we've accomplished here at JPL, when you talk to the people, they had to step outside their comfort zone to think about ideas or even how to implement them. So I think keep that in mind, and of course passion, because the fact that you're here at JPL, you must be passionate about what you're doing.
So we've got 2 last questions in the house that we'll get to, and then we'll wrap it up. So we'll start over here.
Hi, I'm from the education office here at JPL, so thank you so much for coming and speaking. We have many of our students in the audience today, and it's really important to them to hear you today. all of your different backgrounds. That was a great question about interns, and I was wondering if you had something that you could share, just a lasting piece of advice or impression about each of your, we have a project manager, we have a project scientist, an astronaut, and Nobel laureate. What is something that was very impactful, like a one-liner that they could take with them? Many of them are ending their 10-week internships and they're going on to their next steps. Some of them are getting extended. So just something to leave with them as they continue on in their STEM journey.
Something to continue on as they go into their STEM journey.
Okay, I'll just give a quick piece of advice that I learned, that you never be intimidated. I guess many of the questions that you have, some of them people might know when they've been in the field for a long time, but sometimes when people are in the field for a long time, they have been thinking about their own project for a long time, and it is really beneficial for us to hear your insights and your contributions. So yeah, never feel intimidated.
All right, so you've heard about reach outside your comfort zone. There is one other important, at least lesson for me, that I'm reminded by this, like whether, from a project side or science side, you have to be able to recalibrate, meaning you have to be flexible. When you show up to work, you think that plan A is going to work, it's not going to work. Then you have to be flexible to always turn to plan B or even plan C and not let that deter you from the goal. So nothing that we do here is kind of something you're going to find in the textbook. So you have to figure it out on your own. And the only thing that's how you can be successful, whether with the team you work with or in your career, you have to be flexible and able to recalibrate. Thank you.
All right, our last question of the day right over here.
Hello, I'm one of the interns that's finishing in 2 weeks, but I did have a quick question just about the science. So 50 picokelvins, that's pretty cold. I was wondering if you thought that that's something you'd only find in a laboratory setting, or if there's somewhere out in the universe where, because of natural conditions, it happens to be 50 picokelvins. Just curious.
Okay, so if there's I don't think it's going to happen in a natural way, but I don't feel like that rules out the possibility it's finding elsewhere in the universe. If there were sort of the ASF, the Alien Space Science Foundation on some distant star, they easily could have picokelvin temperature there, or the Alien Administration for Aeronautics. And okay, NASA. Anyway, yeah, I think probably if there's temperatures that cold anywhere other than in the International Space Station, it's because of an intelligence that's made it happen.
Thanks.
Thank you. What an excellent final question for today. That is all the time that we have for questions. I want to thank, once again, our speakers for joining us today. I want to thank everybody behind the scenes that make these talks possible. Thank you to all of you and to everyone who asked questions online. As we say, this is your space program. We want you to stay safe, want you to stay kind, stay curious, and we'll see you next time. Thank you, folks.